Okay, so we're going to look at a nice way of evaluating this famous integral using an approach that's a little bit different from the standard approach of squaring the integral, turning it into a double integral, then transforming to polar coordinates. But we will use some of the same steps to begin with, so our starting point is we can note that this function e to the negative x squared takes the same values for positive or negative values of x. So we can actually write this as 2 times the integral from 0 up to infinity of e to the negative x squared dx. We say this is an even function. The contribution going from 0 down to negative infinity will be exactly the same as the contribution going from 0 up to positive infinity. And we'll also think of this as, instead of an integral going up to infinity, we'll think of this as a limit. So we can write this as 2 times the limit as, we'll say, t goes to infinity, of now the finite integral going from 0 to t of e to the negative x squared dx. So we'll actually work with this finite integral, and then at the very end we can take limits to verify the result. And just like in the classic approach where we use polar coordinates, we're going to start by squaring the integral. So let's call this integral, if we say this is it, the integral up to t, so we can write this as the integral from 0 to t of e to the negative x squared dx. But if we wanted it squared, we could rewrite this as the same integral just multiplied by itself. And when we write this the second time, instead of repeating the x, we can introduce a different variable, e to the negative y squared dy. Then you can see how this turns the integral now into a double integral, because we've squared this. We've got 2 different variables. So we can rewrite this now as the integral where both x and y are going between 0 and t, and we've got e to the negative x squared times e to the negative y squared, which we'll write as e to the negative x squared plus y squared in brackets, and this is being integrated with respect to x and y, so we've got our dx and dy. So this all looks very familiar so far, but at this point we're going to diverge from the approach of using polar coordinates, and instead we're going to use series expansions. So we can use the series expansion of e to a number, so we know that e to the power of u is 1 plus u squared over 2 factorial and so on. So we'll write this using sigma notation now. We can write this whole expression as, first of all, if we just keep our integrals between 0 and t, we can write this as a sum, say from n is 0 up to infinity of, we're going to be having this negative e to the x squared plus y squared is our u here, so we've got negative 1 to the power of n, and we can also write this as x squared plus y squared to the power of n, and we just need to divide through by n factorial. And we've still got our dx dy on the right hand side. So we've just rewritten this using a infinite series expansion now. And then we'll do the same sort of thing with this x squared plus y squared to the power of n. So we can use the binomial expansion to help us rewrite this as a sum. So then we can rewrite this whole expression then as the double integral, so nothing changing here, and we've still got the sum from n is 0 up to infinity. We've got negative 1 to the power of n over n factorial, but now we're rewriting this using the binomial expansion as the sum, let's say, from k is 0 up to n of n choose k, then we'd have x squared to the power of k, so we'll write this as x to the power of 2k, then we'd have y squared to the power of n minus k, so we'll write this y squared to the power of n minus k, we can write as y to the 2n minus 2k. So this is, if I just put a box around this is the exact same expression, we've just expanded the binomial there, and we're still integrating this all with respect to x and y. And now our next step actually involves swapping the order of summation and integration, so taking these integral signs within these sums, but unfortunately this isn't something that we can do in general. This doesn't always work for every integral and sum. So we won't go into too much details here, but it does turn out this is going to be something we're allowed to do here. I'll include a link in the description if you're interested, or you could try applying a dominated convergence style argument to show that this is indeed valid. But taking for granted that we can exchange the order of summation and integration, we can rewrite this whole thing then as the sum from n equals 0 up to infinity, taking this sum on the outside. We've still got negative 1 to the n over n factorial, and then we've got within our second sum going from k equals 0 up to n, we've still got n choose k. None of this depends on x or y, So then we can write our integration. We're going from 0 to t for both x and y, and we've got something which is going to be really nice to integrate now with respect to x and with respect to y. So here you can actually see that this integral is a product of a function of x, just x to the 2k, and a function of y, y to the 2n minus 2k. So this is really nice to evaluate. We can rewrite this whole integral then as being the integral from 0 to t x to the 2k with respect to x times the integral going from 0 to t of y to the 2n minus 2k with respect to y. Then when we actually evaluate these integrals, we're going to have x to the 2k plus 1 over 2k plus 1 evaluated at t, then subtract the same thing evaluated at 0, and our contribution at 0 is just going to be 0, so we actually get for x it's just going to be t to the 2k plus 1 over 2k plus 1, and we multiply this by, similarly for y, we're just going to have the t term and the 0 term is just 0, so we add 1 to the power 2n minus 2k plus 1 and divide by the new power 2n minus 2k plus 1. So this is all of our double integral can now be written as this single product, and we can actually simplify our powers of t as well, because we've got 2k and minus 2k. So all of this multiplied together gives us t to the power of 2n plus 2, because we've got the 2n plus 1 plus another 1 there. So this allows us then to rewrite our entire expression then as the sum from n equals 0 up to infinity of negative 1 to the n over n factorial still, and we've still got our sum going from k equals 0 to n of n choose k, but now we've replaced this double integral by a really nice, we've got t to the 2n plus 2 divided by this product 2k plus 1 times 2n minus 2k plus 1. And here you can see this t to the 2n plus 2 doesn't actually depend on k, so we can take this outside of our sum from k equals 0 up to n. So this is just a constant for all of our different values of k. So we can rewrite the whole sum then as lots of stuff to do with n on the outside, negative 1 to the n times t to the 2n plus 2 over n factorial. And the next thing we'll deal with is going to be this sum of all of our k terms, so going from k equals 0 to n of n choose k, then we've got this product 1 over 2k plus 1 times 2n minus 2k plus 1. So our next step is going to be for this 1 over 2k plus 1 times 2n minus 2k plus 1, actually expressing this as a sum of two different fractions, so writing it in partial fractions form, which will allow us to further evaluate this infinite sum. So here the goal is to get this fraction, instead of being a product, as a sum like this, where we need to find some suitable values of a and b, so that this is actually true for all values of n and k. But we've got the issue here that unlike usual partial fractions uses, we've actually got two variables, n and k. But if you think here we're summing over k initially, it makes sense to perhaps treat k like it's our variable, and then our constants a and b will be constants in the sense that they might depend on n, but they shouldn't depend on k, so then we could take them outside of this sum. So let's see where this approach gets us. We want to multiply on both sides by 2k plus 1 times this other term, so that we just get 1 on the left-hand side. So we've multiplied by each of these denominators, then we've got a times 2n minus 2k plus 1 plus b times 2k plus 1. So then if we take, first of all, we've got our k terms, we've got a times negative 2k and we've got b times 2k, so we can write this as 2 times b minus a times k. This is all of our k terms. And then all of our other terms which we're treating as constants, we've got a times 2n, a times 1, so we've got plus a times 2n plus 1, and we've also got b times 1, so just plus b here. So we can think about this comparing coefficients on both sides. For this to be true for all values of k, our k coefficient here, there isn't a k contribution, so this coefficient would need to be 0, so we'd actually need b to be equal to a here. And then this term would just disappear and become 0. So we'd have 1 is equal to 0 plus, we keep our a times 2n plus 1, and then b is equal to a, so we can just write this as plus a. So then we can rearrange this. This is actually a times 2n plus 1 plus another a, so it's a times 2n plus 2, which rearranges to give us a is 1 over 2n plus 2, and this is also equal to b, because we've set a and b equal to each other, so that this is true for all values of k. We need this term just to be 0, so that our constant term 1 is equivalent to this for all values of k. So then when we come to substitute in these values of a and b, we've actually got the same value of a and b, which we can take out as a factor, which means our original product fraction, we can rewrite this whole thing now as equal to 1 over 2n plus 2. This is our a and our b. We take this out as a factor, and then we've just got times 1 over 2k plus 1 plus 1 over 2n minus 2k plus 1, which we can now substitute back into our sum. And we can also take out this factor 1 over 2n plus 2, because this doesn't depend on k. We can write this outside of our sum, where we're summing over all the different values of k. And now we'll focus on rewriting this inner sum in a slightly different way that will simplify even further. So we can take this sum, you see we've got the sum of these two fractions, we'll write it as two separate sums. So we've got the sum from k equals 0 to n of n choose k times 1 over 2k plus 1, and then we'll think of this as being a separate sum, the sum from k equals 0 to n of n choose k times this different fraction 1 over 2n minus 2k plus 1. There's something quite interesting going on with this 2n minus 2k plus 1. This is almost the same as having 2k plus 1, especially as k varies between 0 and n. We can write 2n minus 2k plus 1 as 2 times n minus k plus 1. And then we could actually introduce a different variable. Instead of having k, we can introduce, let's say, m equal to n minus k, so that k is n minus m. And we'll see how this changes what this second sum looks like. So we keep our first sum exactly the same, going from k equals 0 to n of n choose k, 1 over 2k plus 1. But now we've got the sum where k goes from 0 up to n, m, which is n minus k, goes again between 0 and n. So we'll write this, the sum from m equals 0 up to n, and instead of n choose k, we're going to have n choose n minus m, is how we'd express the k in terms of n. So we've got n choose n minus m, and then the upshot of this is that we can write our fraction now. Instead of having 2n minus 2k plus 1, this just becomes 1 over 2m plus 1. So this is starting to look a lot more like the first sum that we've got there. And in fact, with this n choose n minus m term, n choose n minus m, we could go back to the definition of what this means. This is n factorial over n minus m factorial times, it would be n minus m factorial would just give us m factorial, which is the same as having n choose m. So we can rewrite this n choose n minus m as just n choose m, which then gives us a really nice expression for our second sum. You'll see that it's exactly the same as this first sum now, just with a different letter, where instead of having a k in the first sum, we've now got m in the second sum. So we write this, the sum from m equals 0 to n of n choose m, just using this little identity here, and we've got times 1 over 2m plus 1. So you can see this is the exact same sum now. So we can write this whole sum, where we're summing with respect to k, as 2 times the sum of this slightly simpler looking sum going from k equals 0 to m of n choose k times 1 over 2k plus 1. So now when we rewrite this sum, we've got this factor of 2, which is quite handy because this can factor out with this factor of 2 in the denominator there. So we'll replace this 2n plus 2 with simply n plus 1. And now from here, we're actually going to do the reverse of some of our previous steps to get this into a form where we can evaluate this infinite sum over n. And we're actually going to reintroduce an integral here. So we just look at this 1 over 2k plus 1. We can actually write this as an integral. So if we notice that 1 over 2k plus 1 is the same as 1 to the power of 2k plus 1 over 2k plus 1 minus 0 to the power of 2k plus 1 over 2k plus 1. You might recognise this now as the integral between 0 and 1 of just x to the power of 2k integrated with respect to x. So now we can rewrite this whole sum as an integral, and we've got this n choose k, which is going to be helpful as well. So we can write this whole sum. We've got the sum from k equals 0 to n of n choose k times 1 over 2k plus 1 is equal to the sum of n choose k times the integral going between 0 and 1 of x to the 2k dx. And here, because we've actually got a finite sum and a finite integral, it's fine to swap the order of integration here as well. So we can take this sum inside the integral. So we've got the integral from 0 to 1 of the sum from k equals 0 up to n of n choose k times x to the 2k. So you might recognise this as actually a binomial expansion. This is x squared to the power of k, and then you can also think of this times 1 to the power of n minus k, just to make that really clear. So what we've got here is a sum which is actually just a nice binomial expansion, which we can write as, we've got the integral from 0 to 1 of, it's going to be x squared plus 1 all to the power of n integrated with respect to x. So then this gives us a really nice expression which we can use, and then we can exchange the order of summation here for our original integral all squared. So we can write it squared is going to be our sum from n equals 0 up to infinity of, we've still got negative 1 to the n, we've got t to the 2n plus 2, and now this n factorial times n plus 1, we may as well write this as n plus 1 factorial. And then we can replace this whole sum now by this simple integral. It's the integral from 0 to 1 of x squared plus 1 to the power of n integrated with respect to x. And then the next thing we can do is, again, we could be a bit more rigorous with this, but we're going to swap the order of integration and summation again, so that now on the outside we've got an integral from 0 to 1, and just taking this sum and all of these terms inside, with the sum going from n equals 0 up to infinity of negative 1 to the n, t to the 2n plus 2, all over n plus 1 factorial times, when we've still got this x squared plus 1 to the power of n. This is all being integrated with respect to x. So now this sum here is almost looking like an exponential sum. So we've got n plus 1 factorial rather than n factorial, but we've got a lot of things all raised to different powers of n. So that's going to be how we attack this infinite sum and write this in a more usable form. And now just to make it really clear exactly what we're aiming for here, you can see we've got the n plus 1 factorial. So let's imagine we can rewrite all of these powers as actually a power of n plus 1. So let's say we could get this in a form where it looks like the sum from n equals 0 to infinity of something, let's say u to the power of n plus 1 over n plus 1 all factorial. So now this looks like the definition of e to the u, only we've started at an extra term, so we're missing the n equals 0 term. So we can write this as being the sum from n equals 1 to infinity of just u to the n over n factorial. So this is the same as our sum going from 0 to infinity of u to the n over n factorial, but we just need to take away the n equals 0 term. And the n equals 0 term, 0 u to the power of 0 over 0 factorial is just 1. So we just take away 1 there. You can see that this is now e to the u minus 1. So this is what we're aiming for our big sum here. So we just need to make all of these powers of n plus 1 and take out corresponding factors. So if we write this whole sum, we've got the sum going from n equals 0 to infinity of negative 1 to the n. We'll turn this into negative 1 to the n plus 1, which means we just need to take out a factor of negative 1 there. And this t to the 2n plus 2 is handy because this is just t squared to the power of n plus 1. So now we've got t squared to the power of n plus 1. We're still dividing through by this n plus 1 factorial. And now if we want to turn this x squared plus 1 to the power of n into a power of n plus 1, we can write this x squared plus 1 to the power of n plus 1, but now we need to divide through by x squared plus 1. So instead of having negative, we'll write this as, let's say, negative 1 over x squared plus 1. And then this whole expression, we've just got our integral going between 0 and 1. So this is our original integral it all squared is equal to this expression, now integrated with respect to x. And you can see here for this sum, this is now in the right form of what we're looking for, e to the u minus 1, where here our u is negative 1 times t squared times x squared plus 1, so negative t squared times x squared plus 1. So this whole expression then just becomes e to the negative t squared times x squared plus 1. Take away 1. So then we can rewrite this whole thing as equal to the integral from 0 to 1 of negative 1 over x squared plus 1, and then we've just got in brackets now e to the negative t squared times x squared plus 1, take away 1 with respect to x. And then when we expand this bracket, multiplying by the negative 1 over x squared plus 1, we can write this as the integral going from 0 to 1 of, first of all, we've got negative e to the negative t squared times x squared plus 1 all over x squared plus 1. And then for the second term, the negative 1, this cancels and just gives us, we'll write this as a separate fraction, 1 over x squared plus 1. And this is all still being integrated with respect to x. So you can see this 1 over x squared plus 1 is a standard integral, and we just need to think a bit more carefully about this when we take limits as t goes to infinity. So first of all, this integral of 1 over x squared plus 1 just gives us arctan of x, evaluated between 1 and 0. So this will give us a nice way of rewriting this sum in our integral. We can actually write the whole integral as a single integral from 0 to 1. We keep this e to the negative t squared times x squared plus 1 all over x squared plus 1 integrated with respect to x. But then we've just got arctan of 1 minus arctan of 0. So arctan of 1 is pi over 4, arctan of 0 is 0, so we just get pi over 4 from that part of the integral. So now we need to think a bit more carefully, as we're going to take limits as t goes to infinity, and think about how this affects this integral here. And if we consider the limit as t goes to infinity of this it all squared, then we're going to have the limit as t goes to infinity of this integral, just as it was, plus pi over 4. And assuming this limit exists, we can just take the square root of this to get the limit as t goes to infinity of it without the square, which is what we're aiming for. So now as we take limits as t goes to infinity, this integral here, you can see you've got the e to the negative t squared times something positive. So this term is going to get very, very small, and this will actually just go to 0. So the integral is going to vanish, and we can be a bit more rigorous than this. We can think about this as for all values of x between 0 and 1, e to the negative t squared times x squared plus 1 over x squared plus 1. What is the biggest possible value this could take for x between 0 and 1? Well, first of all, with our numerator, the biggest this could be, you want to actually have a small power because it's a negative power, so you would just take x is 0, so the biggest this could possibly be would be e to the negative t squared, just have 0 plus 1. And similarly with our denominator, in order to make the whole expression as big as possible, we want to make x as small as possible, so that would just become 1 in the denominator where x is 0. So this is the biggest possible value we get over all of these different values of x, and this certainly converges to 0 as t tends to infinity. So then we can say that this whole limit then does indeed go to 0 as t goes to infinity. We can make this a little bit more rigorous if you're interested. But then that's telling us that the limit as t goes to infinity of it squared is just going to be pi over 4. So then, now that we've established that this exists, the limit as t goes to infinity of it just on its own without the square root is going to be the square root of pi over 2. And don't forget now we're actually, in order to evaluate the integral we were originally looking at, we need to multiply this by 2 from when we split this up into the positive and negative halves using the fact it was an even function. So we can conclude then, just multiplying through by 2, that our original integral of e to the negative x squared with respect to x is going to be root pi over 2. We multiply by 2, so we just get as our final answer then the square root of pi.